and welcome to Handmade Hero, Shore We Code a Complete Game live on stream. We are going to do some collision detection work today. We're kind of exploring some options that we could use with sort of like the same sort of stuff I did on the Witness, only like trying to do a simpler version. So still trying to approach it from the standpoint of something that we would consider fairly stable. Oops. So something that we're not going to have a lot of concerns about, which is usually the problem with collision detection and response code, is that you end up in situations where your game has all these bugs in it. You see this all the time with Unity and Unreal games. There's just so many bugs with objects getting stuck in things all the time, or falling out of the world, or doing all this other stuff. So the goal here would be to try to move towards a system that doesn't have very many of those problems. So that's what we're looking at doing. And given the limited, on Handmade Hero, everything is very compressed. Normally if I think about I'm going to make a collision detector from scratch, I think about spending several months of careful work on something like that. And we don't get to do that on Handmade Hero. Obviously, you just got to do some fairly straightforward stuff. So, we don't have the luxury of doing something extremely fancy, but we can still try to do the best we can, right? All right. So looking at the way that we're doing this currently, there's a couple things that now if we want to start moving this towards done, I think we should do. At the start, right, you can see I've got this move entity locally thing, and we were subdividing this motion here. And I don't know that that's something we actually want to do yet. So I was thinking about this kind of just randomly in the back of my head. And I think we probably want to now start just doing voxel by voxel stepping. Because there's really not much reason of doing this two-pass thing we were doing. We might as well just start in the voxel we're in and just move ourselves forward along that voxel. Seems like a pretty straightforward thing to do. So I think I might kind of change this to doing that, right? So when we do this movement, we'll just sort of do it one voxel at a time. The way that I might do that first is we just won't move multiple voxels. We'll only move one. And we'll see what that looks like, and then we'll figure out whether we want two routines, one routine that calls another routine to move voxel by voxel, or whether it's all in kind of a loop. We'll see. I don't know. But anyway. So the first thing I want to do is take this move entity locally thing here, and this from P to P. I just am going to say, look, we're not going to do any of this stuff, right? We'll leave the motion displacement size in there, and that'll basically be our voxel size. So our voxel bounds are actually, before we were building a voxel dynamically around the character, and because I want to move this to, like I said, we're going to try and push towards getting this stable now, so it's very solid and doesn't break and doesn't have people getting stuck and that sort of thing. So what I'd like to do is I'd like to say, okay, we're going to now say that in order for our collision, so that our collision detection will be more stable, we're going to always use the same voxel pattern. So we're not going to build voxels based on where you are. We're going to categorize you into a voxel by saying the voxel's always the same shape. It's just which cell you're in is what changes. We don't shift the voxel to align with where you are. This shifts the voxel to align where you are, and we don't want to do that. So instead, what we'd like to do, and I don't know what we've got for math functions. I never remember what sorts of stuff we've implemented on Handmade Hero, But basically, if we have a floor, so you can see here, we have a way to floor stuff, and it's not great. I don't actually want it to floor to an integer. So this is less good. I really would rather be doing this probably. So I might say, let's pretend that we have that though. So I might say like, okay, so there's a floor function here, and it's going to be like f32 to f32, and it's literally just this, right? So I'm not sure what the easiest way to extract this is, but I guess maybe we still just do it this way, right? That's probably the most straightforward way for the compiler to know what the heck is going on. We don't ever want this to come out of the SIMD registers, so like it's not like it needs like this is all just stupid syntactic sugar that the compiler needs, right? So I feel like we need to tell it that we're just extracting the float here, but I don't know. I never remember what these are, right? I never remember what the heck the actual name is for that thing. What's my syntax error here? Just the quotes. All right. So let's see. We've got the convert. We've got the floor. We've got the set 0. So it's probably just the extra one there. So there we go. So in order to do a floor, that's going to get us down to the closest integer boundary. And so what I want to be able to do is just use that to recenter us around where the voxel is, right? And so the problem that we have if we do this floor is that it's not going to be at the right scale. So I want it to be based on the motion displacement size. So I first want to sort of compress this space into something where the integers are along these boundaries, right? So we want to do something that's sort of like, voxel min corner, right? We know that the from P is where we are, right? That's where the thing starts. And we know that if we floored that, like so, we would get the integer base. So if we're at 4.5 or 4.7 or 4.3, we'll get 4. So if we wanted our voxels to be 1 unit long, this would just be it. It would be like this, right? Where we just say, hey, let's just, build a voxel from the floored version and out. So this would work if this were 1. But the problem we have is it's not 1. So before we do the flooring, we need to first compress our space into the shape where integers lie on the boundary, right? So in order to do that, I need to expand, which is the opposite. Like if I multiplied by this, right, I would do the opposite. If I multiplied by this, I would take and I would make it so that the integers were even less correct, right? But if I divide by this, then I am compressing that space into the shape that is, and in this case, that's an expansion, right? Because this is 0.1. So by dividing, I'm expanding it by 10, right? Which makes the integers fall on the 0.1 lines. So if I do effectively the divide versus multiply, right? If we do it like this, that will allow us to produce a aligned version of that, one that is locked down to the closest 0.1, right? And this is really just, we can even, we can treat this as a modulus. So another way, we don't have, I guess, a mod function, maybe. But that's another way of doing this. Like, yeah. So, there's multiple ways you can do it, but there you go. So we floor it first, we expand it back out, and off we go. Now, in this particular case, we want to do this for everything in the vector. So we'd like to have a floor function for the vector, right? Because when we compile this, it should complain because this is not actually mapped across vectors. And, we're in C++, one of the world's worst languages, so it really doesn't know how to do stuff like that. And you have to get into template disgusting land if you want to try and do things like automatically map floor over, a range of things and so on. So unlike a functional programming language where this kind of thing is just kind of handled properly for you most of the time, that's not, where we live in C land. So what I'd like to do is here, where I've got my sort of utility functions of this form, I'm just going to go ahead and add that in there. So I'm just going to make a floor. And again, this doesn't actually do anything. Oh, that's right, I forgot. We don't use that keyword here. I changed to using function. One of the nice things is if you change internal to function, then the same parser can read where your functions are in C++ and in JavaScript, because JavaScript requires you to have function in front of stuff. So then simple metaprogramming scanners will find either one, your JavaScript front-end code or your C++ code, if you use function as a pound to find for that. But anyway. So if we just say, look, let's floor the values in our vector like so, and off we go. Now this will know, like, okay, floor all of these, and we should have something that knocks us down to the closest one, and then we can expand it by that same amount here. And when we look, at the remainder of the code, it now becomes a lot simpler for us, because we only have to test the corners for one. Like, we don't have to do, we only have to test one voxel, right? We don't have to worry about iterating over like a large space or anything. So voxdim here, right, we now know that this will always be 2. We're just going to have like the min and the max of each one. And we also know that the size of the cell is this here, right? So we can just predefine this and it's basically a constant. It doesn't change. So we don't need to compute it or anything. And so we now have the cell dimensions, the voxel dimension, which is always the same. We have the occupied corner codes, and that's it. Right. And yeah, so like if we look, I don't know that we care about this particularly much anymore, but we might. But there's a couple of different ways that we can look at this thing. We can make it significantly more efficient than this, to say the least, but I'm going to kind of leave this in place for now. We'll see what happens. Anyway, we'll start with the min corner. We'll expand out by the cell dimension. That allows us to do, this test is the same as it was, and that gives us basically what the occupied count is. This is still correct, right? It basically tells us exactly which one we want. Oh. That's no good. It basically tells us whether or not there's any. So one of the things we can see very quickly here is if the cell that we're on, is there anything in this cell that we can actually consider a legal position or not? And so when this any open comes back and says there's nowhere in the cell to be placed, that's like a thing that the external, so again, we don't know how this is going to play out, but at the moment, also, you know what, that goes away. We don't know how this is going to play out, but basically what we need here is that would be a clue to the external part of this solver, right? To say you need to take some action to get this object out of whatever it's stuck in. And again, to me, this is, again, crucial to build into the system, because even if we assume that we do our job correctly here, and our collision detector will never place two objects into a configuration where they're stuck, the gameplay code might. Like, we don't want to have to ensure that the gameplay code is smart enough to avoid that scenario. We want the gameplay code to just be able to do whatever it does, and if things happen to get stuck in each other, what we really want is we want this collision detector to be so suave that it will just try to figure out how to get them unstuck, right? So rather than trying to write the whole game thinking that we need to make sure nothing ever sticks, what we're trying to do is make the collision detector automatically unstick things that get stuck in each other, right? And that's just part of making the thing as robust as we can to eliminate as many possible ways that we can screw the player. We don't want to screw up the player's playthrough. That's the worst possible thing that technology can do in a game engine. So we want to try to have it do the opposite. We want it to always be trying to get the game into a playable state. We don't want there to be failure states where, oh, something got stuck because the gameplay code did something and now the game is ruined. Like, we don't want that, right? So, also inline, inline doesn't really exist anymore. So we've just been slowly replacing it with internal. Like, all these can be inline. Can be internal. Really, I should just change it to function, because that's what I use these days. I just put this in front of everything. It's just static, is really what it is. Inline doesn't really work anymore. Compilers just ignore it, so it's kind of pointless. I think sometimes maybe GCC uses it a little bit. Most compilers just ignore it. So, it doesn't really matter. Anyway, so if we look here at this any open, if the any open thing is like we can't find anything, then I think we just punt. So I think here we say if any open, and otherwise we just leave. We don't try to do anything, right? And so one thing we might do also is not move the player also. So what I kind of want here is like a move result, and there's like a found, like we found a place to put it, and here's the place. So what I'd like to do is switch to that kind of strategy. So the entity itself, we really aren't using the entity itself in any capacity other than we need to look at like its collision volumes and stuff, but we're not writing to it. So all we do is we say, okay, we've got a move result we want to produce. We start by assuming that it fails. If we actually get into the any open, then we're going to actually succeed. So we say, yes, we found a place. And then the question is, what is the place, right? So like, what is the actual location that we're going to put the player in? And so this is the part that we actually have to think about. And we are probably going to return some other stuff as well. All right. So this gets kind of complicated. Now we have to start thinking about this voxel in 3 different ways. Number 1 is the easy one, which is, can we place the entity in this voxel at all? Are there any legal corners? Period. Right? And that's the way that we already did. Like, literally, there's many ways we can do that, and we'll probably change which way we use over time here as we refine the routine, but certainly this way works. If the occupied count is conclusive, if every corner, if all 8 of the corners are occupied, then we know that we cannot place the entity in this cell. It's colliding. So this part here is saying, all right, if we could have placed it, then it is possible. So that's the first way we're reporting information about the voxel, right? Or about the collision. That's thing 1. Thing 2 is we need to figure out if we were to place the player, I keep saying player, but if we were to place the entity, because this moves things that aren't the player, so I don't know why I keep saying that. If we are to place the entity in this cell, where? Right? So where would it be placed? And the problem that we're going to have, right, is if you look at the way we're doing this, you can see like we do a get closest point in box, for example, and you can see like we say, so if we produced the cell and we said we wanted to get the closest point to the target point, this would give us that, right? So you might assume, well, use that. The reason that we can't exactly use that is so I feel kind of stupid because if I'm not mistaken, all you would have to do is start at the start location from P, get the closest point to the target point inside the cell, and then just repeatedly bisect that until you found a place you could stand. And that gives you actually the exact answer. The reason that I feel really stupid is because I feel like that would have just worked in the witness solver and would have saved like half the runtime of that solver if I'd thought of that then. Now, granted, all of the stuff I did on the Witness was completely new, and so I was figuring all of that stuff out, and that always is the case. When you first figure stuff out, you don't have the mental model for it, so you're not likely to make realizations. I don't blame myself for that, because the Witness stuff was all very new, very difficult, and was surprising that it all came out the way it did. So no, you know what? I think that it's okay that it wouldn't have worked on the Witness one, because the Witness one requires that the person is standing on the ground. And that makes a big difference, because that means you have to move along a manifold and you don't know what the manifold is. Because this is for floating objects, that's why this would work. It doesn't need to move along a manifold. So I maybe give myself I maybe give myself credit for that. So I wonder about the Witnesses. Why does the player not move on a nav mesh? Then you wouldn't have needed the brute force testing thing. Well, so there's a couple of reasons for that. One is that you still need the way to build the nav mesh. So the Witness does have a nav mesh for like the iPad version, and it uses my solver to build the nav mesh. So you could think of the thing as building the nav mesh, but the reason that it doesn't use a nav mesh for the movement is just literally for accuracy and efficiency, right? If you build a nav mesh, now you have either a very coarse nav mesh that feels crappy, right, which is what you have in like Unity or something, and that's why nobody uses it for movement. They still use the collision detector for movement. Or you have a nav mesh that's super, super detailed, and it's huge and creates a resource loading problem, and it puts stress on the streamer and all this sort of stuff, right? So the beauty of the Witness one is it works in 100% real time. It doesn't have to make a super coarse version of anything. It can let you feel exact movement. It's just better. And there's no baking. It's instant. It's always live for the people who are editing and working on the game. So it's just better, because the Witness one can do either. If you want a nav mesh, you can just take the output of it, and there's your nav mesh. You can reduce the density of it as much as you think you want to, right? Or you just don't bother, and you just let it run on the exact geometry, and it works, right? So it's kind of just a superset of nav mesh. It's just like the better version of nav mesh. If you want nav mesh, you have it. If you can't or don't want to do pre-computation pass, or you want things to be more detailed, or you have tons of dynamic things moving. That was the other thing in the Witness. There's lots of stuff that moves around, elevators, platforms, all this stuff that makes nav meshes kind of difficult, because what do you do at the boundaries between those meshes? You need a solution for that that's rigorous, right? So nav meshes really aren't a solution to anything, to be completely honest. You kind of still need an answer for how do you build the nav mesh, what do you do with all of your dynamic stuff, blah, blah, blah. And so the Witness thing is just the superset solution. It's like, look, this just works, right? And if you want the features of a nav mesh, you can get them. If you don't want to deal with all of the drawbacks of nav meshes, you just don't have to. You can just not do that. And in the Witness, we did both. So in the Witness, for click to move, you want a pathfinder, so there's like a rough thing that's that, right? Me and John Blow are on the same team spiritually. We're not on the same team physically. All right. I wonder if what I just said actually works, which is kind of nuts if it does. So, I don't know. I don't know, but it kind of feels like it would. So, I guess what I'm trying to say is, like, suppose that you pulled this piece of junk out, which is the part that we want after we're done making sure that this routine works well. It's the part that we'll replace with the spatial partition, because this is the core cost of this routine, and this ain't gonna fly, right? So this will be a local lookup that just gathers the things that are right next to you for testing. And so we want this to be isolated probably for other reasons anyway. But assuming that we just do a thing that's like can place or collides at P or I don't know what, assuming that we have this and we put pass in the stuff that we need for determining whether you can stand somewhere, right? So you basically say, like, you know, here's the thing, this will be, you know, a space partition thing, it's at some point or something, or this will just have space partition built in, we don't know, who cares. The entity goes in here, the P that we're trying to test goes in there, and we literally just go and say, all right, this is the rectangle testing. We would iterate over the spatial partition. We see whether or not we're supposed to have a collision here. We do that test, and then we produce the result here. So, you know, we would do a thing that's like result equals false. It does not collide. Here, the result equals true. It does collide, and that is the loop. So in here, we would say, rather than all this stuff, we just do this part, just this test, and we call out to collides at P, and we say simregion entity test P. Now, you may be, why did we do that, right? Well, now I can call that in a refinement loop, right? Who is Biddle? It's not like Mike Biddlecombe, is it? No way. Really? You serious? No, you don't need a code word. Well, great to see you. How's it going? I think the last time I saw you was at Handmade Con. 2019 would have been the one. That was the last one that was like in person, right? How's it going? What are you up to? You in Canada now? In the great northern expanse? Or are you back in the States? Mike Biddlecombe, ladies and gentlemen, he is person I worked with a long time ago. He is from Canada, but he was working in the States at the time, and then he went back in Vancouver. Yeah. Vancouver's a really nice place. Anyway, thanks for stopping by, Mike. Good to see you. So the thing that Mike Biddlecombe was amused to see me realize, is if we are moving in 3D, it means that fundamentally we don't have to move across any particular manifold. Like, we're just moving this thing across space. So once we know, if we test the sides of the cell and we just make that be our criteria for are you allowed to move in this cell, we can then place the person, the entity, anywhere in the cell, right? Because we know that the rule for could you be in this cell is are any of the 8 sides of the cell vacant or not, right? So then we can just do, hey, if we know that we can place a person in this cell, let's just root find to find out where, right? Now, there is one case that this won't handle correctly that we'll have to think about, and that's if the place that you're in, if you're already in, actually, it'd probably handle that too. So if you're already in, then you just look for the out position. This might actually be really awesome. So here's what happens. You now have the cell. The cell doesn't, this is stupid. We don't really need this. Because there's only one cell, right? I mean, we stopped. You've got a min and max corner, so like the cell is just that, right? Because we're only doing one now. So in here we go into the routine. We check to see whether it's legal to place anyone in this cell at all. We can now just root find to see whether we can where in the cell we can place that's closest to where you were trying to go. And I don't know. I can talk a little bit about why I want to do that 2-level thing, because you might be like, well, why not just do that root find in general? And there are reasons I don't want to do the root find as the definitive thing, because I'll talk a little bit more about why I think we want 2 different rules for how that would work, is all I'll say about that for now. Okay, so let's suppose that we then go ahead and want to do this test. So if we do a collides at P test to see about where we're standing, so the from position, like where we are, right? If we look at whether or not that's in or out, so starting state is this. So where we are standing, we know the starting state. In the future, we can probably elide this. So we probably know which one that is because the last thing told us. But for now, we'll just recheck it. So we look and we say, are we colliding? And then we then binary search for a place where that's going to be where we satisfy the other criteria, right? And the only thing that I think we probably want to add is some awareness of the state of the voxel sides. So if all of the voxel sides, I'm not sure how I want to use that information in this part, so I don't know yet. But point being, in this case, we know what our starting state is, and I want to do a refinement here. So there's just going to be, a few steps of refinement, and I don't know how many I want. This is basically a tolerance that can be like cranked. And so what we can do is, as we do our refinement, we will bisect the difference between our from P and our to P to get like a place where we think we can stand. So the this would be like the test, the T test, right, is going to start at 0.5, let's say. So then to compute the test point, we're going to do a linear interpolation. We still need this. So here's the like local target P, right? I mean, I guess this is like the place we're trying to get to inside the cell. We can't leave the cell. So we're going to say, all right, the local 2P. Oh, and there's one more thing about this too. So there's even one more thing, which is do the refinement step only at the end, right? So another aspect of this is actually this probably doesn't have to happen. We probably can just do this at the end. So the refinement step only happens in the final voxel cell, right? So to me, I think it probably looks more like this, where we only do, we first do the voxel to figure out which voxel you're in, and we let you move through there. And then here we just say, oh, okay, at the end of all this, then we take and we do, we assume that you pass in the voxel that you're talking about. So this is the cell. We assume that you're going to have the stuff that you needed, which obviously, you need this stuff. So at the end, after everything's done, when you have figured out what voxel cell you have determined that the player or the entity, I should say, will end up in, then you call refined voxel placement only on the final cell, and then what you do is you take that target location, you see where in the cell that would map to, the closest point, and then you refine towards that to place the entity as close as possible to the correct position. How do you like that? That's a good spelling there. Doesn't matter. Okay. So what we want to do is we are trying to find, I guess, I'll show you why we need this in a second, but assuming that we started out in a position where we weren't, right? So we could just say, like, assert starting state equals, it's not colliding or whatever, right? But assuming that we started out colliding, the reason that I need to know that is because if you think about the binary search process that's about to happen, what we're doing is we're saying, all right, there's a test point. We're going to start in the middle. We're going to take the local 2P, right? And we're going to linear blend. Do we not have a linear blend? Okay, it's called lerp for some reason. So if we take a look, we can call lerp to use the t value to say where from, the starting location to the local target, right? We take a half step, and then on each time we say, for that test P, does it collide, doesn't it collide? Oops. So we check to see whether it collides. If it does collide, let's pretend that we are not going to use this yet. We're pretending that we always start safe. So we start uncolliding. If it does collide, it means we've gone too far, right? We've stepped into the colliding zone. So we need to step back. If we don't collide, it means we could potentially go further. So we need to step forward. So what we want to do is say like, oh, okay, our t-test is going to have a step to it. That step is going to start out at whatever the half is, and each time we're going to shrink it by half, right? So the t-test is going to take, and we're going to add or subtract one of those two things. And I don't... I think we probably want to do this. So I think we probably want to do something like... we want to take t-test, and we want to say that like t-test equals like t-test plus collides. Or, you could do this like we make the two steps here. So there's t forward, t backward, right? Or maybe like t collides, t safe or something. I don't know. And these are just t-test, like if we collide, it's like t-test minus t-step. And if it's not, it's plus t-step, right? So if we collide, we come back. If it's safe, we go forward. And so you can see now why I want this starting state, because if I know that we're in collision to begin with, it's the opposite. So I need to do a thing where at that point I say like, oh, if the starting state actually was colliding, then the t-step is the negative, right? We flip it around so that when we add, we're actually subtracting, and we subtract, we actually add. So we assume that the starting state is clean in most cases. It means that t-step will be positive in most cases, which means that when we look and we say we collided, right, we want to step back. So it's a minus, right? Okay. So that also means this is branchless, which doesn't matter because there's a ton of branches probably in the collision detection part of things, but we can optimize it. We can do whatever we want. We've got lots of options. Anyway, so if it collides, we will t-collide. If it doesn't, we will t-safe, right? Those are the options that we had, and this will route find us to the best position to place this thing, like the result, right? And so at the end, we sort of have our last best position that we didn't collide. So we can save, right? Like we can say that we have a result P. It's going to be equal to where we started. Each time here that there is a safe place to put this. So if we say like, if we didn't collide, then the result P equals the test P, right? And so again, we can also phrase that this way, just in case we want to try and be squinky about it. If it doesn't collide, or we can still say if it collides, we take whatever the previous result was. If not, then we take the new one, right? All right, so this is the iterative refinement step. So again, just so everyone, I realize collision detection is very difficult. I realize all this stuff is really complicated. So I apologize for that. But, what can you do? Let me explain briefly what's going on. One more time for folks, because like I said, it's complicated. So, I've got it in my head and I'm working it out, and I'm trying to explain it as I go, but I realize that like I'm seeing pictures that you're not seeing in my head, right? And so that's why we go to the light board sometimes. I don't really want to do that right now, but if we do refine voxel placement, what we're basically saying is we've determined that we can place the player in this cell. And the reason for these two things, and we also need, obviously, to make this loop actually work, we need to half it each time. Anyway. So we do refine voxel placement. We come in here, what we're saying is it's legal to be placed in this cell. So we've determined that we can place the entity in this cell. That means that that cell is traversable, and so we're not going to worry about where in the cell you place the entities as being legal or illegal, right? We're saying you can place the entity anywhere in this cell because the rules of how you move things allowed that to occur. So now all we're doing is trying to get a ballpark figure for where in the cell it probably should be. We don't care if we overshoot or undershoot. Like if there really was something that you could have you could have moved around in the cell, or if you allows you to tunnel through something, that's fine, because we're actually handling the legality of that at one layer up. We're basically saying, look, the voxel pattern is what determines where you can place stuff, right? If that makes sense, right? So that's how we're going to do that placement there. And again, that's because one of the things that I really think is important for collision detection work in games is accuracy is not at all what you want. What you want is that things always can get out of being stuck. So you pretty much don't ever want to be thinking about things like, oh, at a very small scale, I need to find exactly where this can move and I need to prevent it from going through other things. You're just setting yourself up for everything getting stuck. What you want is coarsely, can the thing be roughly in this area? If it can, place it reasonably and allow yourself a lot of freedom to place it anywhere there. Because you need to give the collision detection response part of the code as much opportunity to get things unstuck as you can. So focusing on accuracy of whether or not two things could have moved past each other or could have done this or that is never really a good idea, in my opinion. You want to focus instead on options, giving the collision detection a lot of options to put things somewhere that works. So that's mostly the way in which we're approaching this. This routine is just for iterative refinement. It's to place something in a more plausible location to the viewer's eye, is the way to think of it. It does not, we don't want it to control whether you could do something, right? It's just to try and give the most plausibly visually pleasant result. So that root find is there for that, and that alone. We don't know what we want this to be. You could, if you wanted it to be accurate to floating point precision, you could do that, right? And now you're out of precision. Your floating point numbers can't really do any more than 24 bisections. I don't know that we'll need that many. I'm going to leave it at a low number for now. We might crank it up higher once this has a spatial partition so it's fast, right? But right now this is going to be dog slow because each one of these calls is going to have to loop over all the entities, right? So we know it will be unbearably slow to start with. So I'm not going to crank this up or try to find what this number should be right now. We're going to do the spatial partition before we play with that. All right. So refined voxel placement. We now know that we can just call that at the end. And so we know that the end of this routine here is just going to look like this. So the refined voxel placement part of this here is going to have all the stuff it needs we assume we're sort of setting a target now for this. By the time it gets into this routine, it should have all of these things. The cell in which we would like to place the entity, the region, which we know because that's already, just a given. The entity we're placing, obviously also known. And then the 2p is always going to stay the same. That's where we want this thing to end up. So that's a separate issue we don't have to touch. The from p may have translated. It may have moved from cell to cell as we go, right? So that part is also sort of a little bit different, and I'm not sure how we want to handle it. One way would be to map it into the cell at the beginning as well, so it just teleports to there. Another way is it gets convected along in like the center of the voxel faces as we go, and we assume you had to come around that way. That's arguably the more accurate thing. I just don't know if it would ever make a practical difference. So it might just be a lot of bookkeeping that's happening for no reason, right? And that's a really hard judgment call. So I suspect what I'll do to start with is I'll just say, look, the first pass of this thing is going to be we're going to map in that. And you know what? The heck with it. Like, let's do that both sides. So the 2p here, we won't do a local. It'll just be assumed, right? So we'll just say, like, note, it is expected that from p to p have already been mapped into the cell, right? So we're just not going to do that part. That part has to have already happened. So in here we have both of these now. We'll map the from and the to, and we'll pass both of those in. And that's just how we'll start. And this one is probably just right. Like, that is probably how the routine should work. This one might not be. So, right? So Harry Studios, I study cinematography for rendering reasons. So when it came time and I said I'm going to upgrade the actual look of the webcam, I was like, let me light this as if it was going to be a pro-grade thing. And I don't want to give away too many secrets, but let me just say that I guarantee you that nobody else in the world did lighting the way I did it. It is a technique I have never seen mentioned anywhere. I was very proud of it when I came up with it, because I was like, that is really good, and it worked very well. I was inappropriately proud of my lighting, my idea for lighting, and I'm glad you liked it, because I thought it came out really good. All right. So yeah, refined voxel placement. Move entity locally. So yeah, I guess now we just need to do the pathfind part. This part's fine. This now just goes away, right? So we're not going to do any of this. That goes away. And so what we're going to do here is, this is the most sensitive part of the, this is the most time, like, continuous stuff is usually better when you're writing it. You just do float computations and it works, right? The discrete part is always the part where things get hairy, because this is bookkeeping. And so what we need here is we need to start inside a voxel cell. We need to figure out which direction in voxel cells to move. And the really annoying thing is we need to figure out a way to figure out when to terminate, right? So I mean, maybe the answer is you terminate when the closest point would be so I think you're going to want to do something where you basically say, look, we look to see what corners are open. We allow movement to the neighboring cells that have those open corners. And the problem is just knowing when to stop looking at cells. I mean, I think what you would do, I guess, is you say, look, I move towards the cell that is the closest one to the target point on each step, and I stop when there are no cells I can move to that would be closer than the cell that I'm in, and then I refine. Yeah, my glasses broke. I talked about at the beginning of the stream, my glasses broke, and I only need correction in one eye, so I just kept the one, and I ordered new glasses, and I'm like, now I'm a monocle. I'm the supervillain I always wanted to be, but now I gotta wait for new glasses to come and get delivered, right? I'll do a stream at some point. I'll try to put up a video separately that like talks about how I did the lighting. I should probably do that. I should put up a video that's like, all YouTube, and it's like how to make the perfect lighting for $50 or whatever, right? And it's got like me like on the like as a little thing on it, and it just says $50 lighting or whatever, $50 perfect lighting, no way, or whatever, right? Or like that stupid crap. That is like what we need. And then there can be like real cinematographer reacts to Casey's crazy lighting setup or whatever, right? Like and then someone else makes money off the video, and we all make money off of reacting to each other's stupid idea, right? So I agree. There needs to be arrows in the thumbnail. For sure. For sure. Get cinema quality lighting with this one weird trick. All right. So in the move entity call, I think what I want to do, right, is say, okay, so this thing, like I said, I don't know what these routines are going to look like, but it's sort of starting to fall into place now, right? We kind of know that this is what it is. That looks right. It doesn't really need to be a separate routine. It could be moving, but it's well enough, it's fine. It's well enough, like, constrained and contained there that we can leave that way. This is now probably just actually the routine. So I don't think we're actually going to want to call, quote unquote, this or any of that stuff. So I think we're probably going to want to just do it right in here. So I'm going to weld these routines back together again, like we had actually pulled that out, and I'm going to stop doing that. And I think we're now going to do the setup in here. So the cell dim is always the same, right? That's the size of our voxel, and off it goes. And then I'm going to have a for loop here, right, that's just going to loop until it can't move to a closer cell. So we'll have some metric, maybe from the center of the cell to the target destination or something. And this is kind of the part that's a little bit tricky. It's like this is why I didn't immediately weld this routine in. We may want to call this routine to get better answers by doing the refinement on more than one cell. Because if two cells are within a certain, we don't know how close we can do in each one. Oh, yes. The tip professional cinematographers do not want you to know. That is, yes. That is it. Right? All right. So if we assume that we are if we assume that we're going to take this and loop through and move, really the only problem is making that judgment call, like I said, because everything else now I think just sort of happens. So we kind of have this idea of a of a walk point, like we're walking through this voxel, and I don't know what this is for. This is just stupid now. That is true. That's a true. That to do is not a joke. So that's there. But we're going to go ahead and start with the walk P thing, and we're going to say, all right, we have a walk P that's the point that we're testing. And maybe that gets like recentered in a way. So, maybe that just walks from cell to cell. In fact, that's probably what we do. So we start this way, and say, yeah, like we're going to start the voxel min corner, voxel max corner thing, and the walk P would be like there. And we're just going to move that by cell amounts, right? So depending on which direction we want to move this thing, it's going to be something where we just take steps in that direction, right? So it's going to be like walk P, dot x plus equals, sine times cell dim x, right? Like it's going to be this kind of thing where we're just stepping through and the cell itself, like this thing is just going to be like offset in the exact same way, right? So we almost don't need the walk P, right? That's just a way of getting the center. So this could be in here or whatever. So at some point we then say like, okay, like displacement or like next step or whatever is just going to be a thing that we offset the cell by, so we step each time, and the step itself is just determined by which direction we're going to go. So we do like one of these, you know what I'm saying? We'd step in one of these directions. Does that make sense? No. Malice Bixie, what do you mean the divide outside the floor? Oh, yes. Man, you guys are catching good stuff for me today. Thank you. It's been my brain's pretty slow today. I think because I was up too late last night playing Satisfactory on stream. But yeah. As I said, you want the divide, then the floor, then the multiply is the goal. Right? Okay. So we can build the cell. This Is rect min dim actually? So you know what? This stuff we can do this. That way we don't even have to do the offset part. We just say voxel min corner plus equals step. That's just better, right? And furthermore, we can actually just ignore the step part now and do what I wanted to do originally, because if we just have a vector, we can just do something where we're going to be stepping the min corner, and then we just, each time we build the cell by just stepping out by the dimension, right? So, I think we're narrowing in. So here we have the whole, like, occupied, in unoccupied sort of thing. I don't think we want any of this now. Is all just not there. We may want to continue drawing the outlines, though. So that part may want to be there. But yeah. So then let's see what else we've got. Okay, so we have our for loop. We've got, yeah, that's all just kind of garbage. The cell here, we do want to exit with it. So we can, I suppose, recreate it here by just saying, okay, the cell, you know, we produce it by doing the min corner add the same way. From P and to P in this case, this is just the entity's position. This is just the target. So I think that's just this here. It's just that, right? It's just the delta P. So we didn't actually record this anywhere, but we kind of just want to make that a thing. That's where we were trying to get to, you know? And so I think that's everything for the sketch of the routine. And now we just need the actual way of knowing how we step through the voxel, and that's, like I said, the tricky part. So in here we would then say, okay, and you can also see where we can save a lot of time here, because we can also keep a bunch of our occupied stuff. Right? If that makes sense. Oh, yeah, the return statement, it doesn't complain about the return statements till you actually get a compiling program. That's just one of the things Visual Studio does. It, like, doesn't get to that stage of compilation or something. So it would have said, hey, you gotta, it would have errored. The reason it wasn't erroring is Visual Studio just doesn't do that till you get the program linking, like, basically, to the stage of linking. So, okay. Let's go ahead and figure out how we're going to do this part, because this is by far the hardest part, I think. So we figure out whether the thing is occupied, right? We know that if there's nothing open, I think we're probably going to have to do something like this, right? So there's going to be like a best cell thing. And honestly, that's probably this to start with. So we assume when we start that the best cell is just the one you started in. And so if everything just fails, you just end up back in that cell, right? And that's it. And we'll have to work on what happens in that case also, because remember, we have to handle the case where we're trying to get out of something, as well as the case where we're trying to get in, like, or to avoid getting into something. So this is probably now going to just be like, yeah, whatever the interior part of the routine tells us is the best place, that's what we actually need to work with, right? So inside here, what we're going to be doing is trying to find that best place. And so when we look at whether the thing is has any state occupied. I think we probably need the same sort of idea here. Remember I said I have the to-do up at the top. It's like, this can probably be passed in. The reason I said that is because I was pretty sure that we would need to do the check up here. And so we would be keeping a running check of whether the from position is actually in or out, right? So let's call the from P here. Let's actually call that from P to make it a little clearer. I just feel like that's maybe a little bit better. So you can see what's going on. But we're going to have that start location, and I want to know whether we're colliding, whether we're talking about getting something unstuck or preventing something from getting stuck on its way to wherever the target is, right? So if we assume here that we've got a start collide, right, of collides at P. So in here we say, yeah, like, hey man, were we inside or outside at the start of this? And this is going to mirror sort of what we were doing here. So in exactly the same way that we basically flip the refinement, in the same way that we flip the refinement, in this version, we're going to do the opposite thing. We're going to flip the rule about where we can go. So what we want is from now on, like in here, what I'm trying to say is like that one test, are we inside or outside when, like, are we colliding or not at the start of the move, effectively acts as like a giant knot, right? It's going to flip what we consider the place we can move to or not move to. So if we assume that we started colliding, we're going to want to allow you to move out of any cell that we want to allow you to move through a cell that's completely colliding. So when we look and we see any open, normally if any open is false, if there's nowhere to place the player in this cell or the entity in this cell, that means we can't consider that cell. But the opposite will be true for any condition where we were colliding to begin with. Then we want to we need to be able to tunnel through things to get ourselves out of stuck into something valid, right? If that makes sense. So yeah, you know what I'm saying? It's tired in here. All right. So again, the hardest part of the routine by far now coming up for sure. This is going to be the tricky part. Let's start with the easy case, which is, well, this is the easy case. Neither of them easy. Let's start with just handling one of the cases. So although I know that I'm probably going to want to use that as a switch to change what happens in the selection path here, we're just going to assume that this, for now, is always false. So you're starting from a legal position, and we don't have to handle the case where you're trying to get out of a place. So at that point, if you always assume, temporarily we assume, that we only move you to cells that are going to be closer, and that the only thing, let's just assume, let's assume that we don't ever care what the refinement will actually be able to do, which is possibly dicey. That's why I say we may need to call that routine to check a couple different cells to see which one would be the best. That can be like an upgrade version of this routine. But at first, let's just assume that each cell just has a, when we do get closest point in box, right, that the points we evaluate are just the closest points on the box, and we never move you to a cell that is less close, right? So if we look at what happens, there's, for any point that we're looking at the voxel, we never want to move you further away from the point, right? So there's only going to be 3, let's say 4 cells you could move to. I mean, we really could say 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8. So we could really say that there's 7 cells you could move to, right? And so I'm kind of thinking, look, as we check to see whether you can move, whether you've got the option to go to different cells, maybe we just loop through those here and then consider those cells the best possible next cell, just based on whichever one contains the yeah, I'm sorry. I just don't know. I just don't know what the best way to write this is. I'm going to have to experiment a little. Because, like, another way to say it would be, like, maybe you just want to look at the corner codes and move as many of the axes you could move towards the destination. If the corner codes would allow that move, then you do that move. You know? So you move along X, along Y, along Z. If those are available, you just do that. So let's just not overcomplicate it then. Let's just see. So I'm gonna then say, look, let's say we look at what these codes are, and we had a thing. We sort of did this before, so we're doing kind of a slightly similar thing. But we want to know, like, can we move in X or not? Can we move in Y or not? Can we move in Z or not, right? We just want to kind of know which directions we would be allowed to move in. And I guess we kind of also want to know if we can move diagonally. And we could, you know, and I don't know, like, if we want to allow direct diagonal movements. It seems like you probably do. You would just say, if the corner is open, right, like you do, so, like, if if you can move through the corner, you would look literally just at the corner. And then for moving in the but for moving along just the cardinal directions, you would look to see whether the you would look to see whether or not anything on that side was. So this is like a corner move, right? that is a move in Z. So you're basically saying, like, is there any way I could get out of this cell in the Z direction of the target, right? And you would do the same for each. Hopefully this makes some sense. So quarter move, Z move, Y move, X move, and you know that you're only ever going in one of those directions. Like, you're never going to go away from the target point, because presumably whoever asked you to move in that direction doesn't want you to move in the opposite direction, right? Like, that's never something the gameplay code wanted to happen, right? So that's the idea, and this would allow us to test each of these potential moves, right? So we can then actually do that. Like, we can test each of these and see whether they are better or worse, and then we just accept the cell that would give you the chance of getting closest, and we don't actually check first. We don't actually see how close you could really get inside that cell. You know what I'm saying? And so then we just accept that move if none of these moves would produce a better result. So if we get down here, and we say there's nothing that would put us closer, right? That's the criteria for breaking. So there's like, if, you know, a move exists, then great, we do it. If not, then we stop. You know what I'm saying? At that point, like, occupied count maybe just doesn't matter at that point. So maybe I just don't care about that. That's a good question, and I don't know. So we'll see. I'm not going to promise anything. That may come back, right? And the answer here hopefully is yes, because this is asking the question of, can we implement the thing we are literally trying to type in right now? So hopefully the answer is yes, because if the answer is no, we're going to be very sad, because it means we can't do what we're doing. But, you know. And so let's put this down here, because this is really just a little variable that now doesn't even have to be a pound define. So that can just kind of hang out there, and we'll decide what to do with it later. So that's all good, and now we just have to write the code that actually checks for the movement. If we look here at this stuff, this is sort of, yeah, like what the step would be. So I don't know how we want to do this, but it's probably something like this. So yeah. Maybe we'll just call this direction. Right? So if we end up with a movement, and we could even just do like if dir x or dir y or dir z, right? So if we end up being able to move, this is not a great way to do this, but if we end up being able to move, then we move. If we can't, then we can't, right? So we've got something that looks sort of like this, or whatever, and really, I want to say that this is really just this. So the same thing that we'd be setting here. I mean, we probably just don't want to do this, but like, right? It's just a sign. It's just the same thing we were using to make that variable. It's kind of annoying, right? But whatever. So in each of these cases, it would be like this sort of thing. Right, so the moves, if they're allowed, are these moves. And like I said, excuse me, the problem that we now have here is we need a thing that actually tests to see which of these moves is actually better, right? In each of these cases, we want to actually try to produce a better cell for the next time around. So we probably just want a function that kind of wraps this up for us. And in fact, maybe we would just do... Maybe we would do a thing for now, because this is, like I said, it's kind of hard, this routine. So let's just kind of break it down and make it as simple as we can. Let's do a thing where we say, okay, we've got the we've got the min corner is here, and the best distance squared is in there, and then we just have a function we can call that will update this thing. And furthermore, maybe that has the moved in it, so that way this thing doesn't have to do something nuts like that. So that is sort of what I'm talking about. Each one of these would be like update best, and it would be that sort of thing. So we just say, hey, update the besties here, and each one of these just passes in the like vector that I was gonna try and use to update the thing, and then we just kind of jam all the stuff into the best function, and this allows us to like write this code that, you know, we probably need to do a better job on at some point, because this is just a lot of stuff happening in a thing we need to probably be somewhat fast. But that is more or less what we need, right? We then don't need this, so we can probably make these look that way, which means this can just pass dir directly, and this can pass dir by component. Which looks a little better. And then here we just need the sign. So, you know, this is just the sign for 0. Yeah, so this is just, I think, the sign or 0 of the delta. So the direction you're going, or trying to go, the sign or 0 of that, which I guess we don't really have here. So we don't really quite have that. So so I'm not sure exactly what we're gonna do here. We're gonna think about that separately. I guess I don't care. I guess we just probably don't care. Because we're just testing these voxels for being closer. If they're closer, they're closer. We don't care about the fact that if one of the we don't care about the optimization that one of those steps might not need to be tested because its movement portion of the movement vector was 0. So I think maybe we can just skip that. Probably and be fine. But there's other things we want to do here, which is we need the thing for this. So we need the side part of it. So we need like the side part as well. And that's just like, you know, this actual testing. And since we're going to do that, I suppose we can just go ahead and compute both of these. So we can just say, yeah, like, let's use delta p is the thing we actually need. So maybe we just do dir and side, and we just go like, look, if dir.x is less than 0, I'm sorry, if delta p.x less than 0, then dir.x equals -1, side.x equals 0, right? And the else clause is the opposite. So, you know, we can do that. And if we wrote that out maybe more concisely, it would look like this. So, -1, 0. Sorry, -1, 1. Something like this. And then this one just looks like the exact same thing. Again, just random. I'm not sure what the easiest way to put in that information is. There's a lot of ways we could encode that. But basically, that's what we need. We need to know what direction we're going, and we need to know where to look up in the voxel occupancy for testing, right? So then when this happens, we would call update best with that best thing. And here would be the update best part. We need the voxel move here. We need like this to probably be initialized to F32 max, right? So when we actually start this nonsense, we would say, well, the voxel move that we're going to try, the best distance squared is, maybe this is just distance squared, is F32 max, and everything else we need to fill in here. So we're gonna need the 2p, like where we're trying to get to, the min corner, and the cell dim, right? And these are not actually going to get copied. They'll just be kind of filled in because hopefully this would all be like inlined away. But again, we're not really trying to make this fast yet. So one step at a time. All right. So in here we have voxel min corner. We have, I mean, actually, I guess we can just have the cell. Well, no, we don't need that. So I think that's what we need. The distance squared thing is just going to be distance squared there. The following we're just doing conversion of int to real. Oh, all right. The question mark operator in C is so unsatisfying sometimes. All right. All right. So in update best, we know we need a direction, and we know that we need to set all this stuff up for it, which I think it now would have. So what it would do is it would go, okay, suppose we made the test cell, and the test cell is going to be a rect min dim of the move the move min corner plus the offset. So that the new min corner, or the test min corner, is the current min corner plus the direction times the dimension of the cell. So that's where we would move. The test cell, therefore, is that min corner plus the dimension. And then we would say new, or test P is the get closest point in box. So if we said inside that cell we're testing, what's the closest point to where we're trying to go? And then the test dist squared is going to be the distance squared of the place we're trying to get to versus the closest that we actually got. So the vector from where we could get to where we'd like to go, that's the test distance squared. We then just accept it provisionally. So if the distance that we had before is not as good, then we accept it. Right? Now the problem is we need to accept the min corner. We need the base min corner for the other people who are moving. So this has to be orig min corner and best min corner, right? Because these are two different things. So we actually need best min corner because we don't want to check off of that. We want to keep the best min corner moving while the orig min corner stays where it is. So I think it looks like that, and then in here we have to set these. So the best min corner we don't really have to set, but we might as well. And then this goes ahead and does the updates. Eventually it says, okay, if we got one, it just takes the new move. If we didn't get one, then we just assume we can't keep going. So we stop, right? Yeah. So anyway, oh, and here's that return. Remember I was saying, like, once you actually get a linking program, it'll complain. See, there it's complaining because we didn't return result, right? So anyway, that is my argument for roughly how this routine would work. It's probably not very good yet, but hey, for one day's work, that seems okay, right? Like, it's okay. So now we have to start probably like stepping through this thing and cleaning up our bugs and whatever else has to happen there. But that's the idea, right? So what we want to do is we want to set a breakpoint in here. and we want to step through this thing, and we want to see like what the heck is going on, right? Yeah. So like we're doing this, right? And we loop through here, and we see, I don't know what this looks like, but let's take a look. So this direction is 1, -1, 1, right? So, oh, we must be compiled in release mode. That's not going to go well. Seems like that happened an awful lot of times. It should have only happened 8 times, but maybe it may have unrolled this loop. So let me, I want to step into this so I can watch what happens and clean up stuff as we go. So here we go. So let's take a look. Like, here's from P and to P. It's a very slight motion. Slight motion in Y. We're going from to this looks right, that's -1. And voxel min corner looks correct. Because we're on 0.1s. 0.1 is stupid. Before I go any further, I think I want to not do that. You don't pick a decimal on a binary machine. It's just dumb, right? So maybe we say like something that's an actual a close to power. You know what I'm saying? So that it can be represented properly. So that way it's the closest point, like 2.5 or whatever. And now you can see like how much nicer these numbers are, right? They're exact because we picked a power of 2 instead of a thing that, oops, I don't know what I just did. Like cleared that number or something. So that's just probably better, right? So, all right. So we pick a min corner that looks correct to me. Yeah, I mean that's the correct min corner. So I think we're good, right? We look to see where we're trying to go 1, -1, 1, right? We look to see whether those are not occupied. I guess they're not. I mean, we can see it looks like this is free movement, right? So you're just allowed to go wherever you want. So we're saying that you can move diagonally, right? And you don't actually want to in this case. You only want to move in Y. So this isn't a good move, but it's allowed, right? So we then say, well, all right, if this is the move, we take and we make a test min corner that is the original min corner. It should be 0.2 in each direction. It is, right? That's exactly what it should be for the diagonal move. You create a test cell. You get a test P out of that. And the 2p, I don't know, we can't really do the subtract. I'm gonna, so just to make debugging easier myself before I finish this, I'm gonna do like a delta p here, just so I can inspect what the difference is between the 2 points that it's looking at, without me having to go do that math in the debugger myself. So I'm literally just replacing what was on the interior here with a variable that I can inspect. Just, hey, because debuggers still really aren't what you'd like them to be, so you have to, like, manually, a lot of times, move your code around to, you know, make it easier for you to watch what's happening. So if I go ahead and step into update best now, I can look and see what that delta p is. And what you can see here is the separation is a little nonsensical. I'm not sure about this. I want to verify that this is right. So the test cell in this case you're trying to get here. I just realized what this is doing. Okay. What I said was totally false. You don't want to start this with F32 Max. You need to start this with whatever the closest thing you've ever seen was, right? And you need to keep that through the entire time, probably, right? So you're probably going to do something like this, where you say the best distance squared is actually like the distance from the best point on this cell. You know what I'm saying? So we say, you know, the distance squared is the distance from the get closest point in box to the 2p, right? It's actually like from where you are right now. So the starting cell that you just initialize into, you probably need that as your test, because you don't want to move out of the best cell that you had, right? So I think, let me just double check here. I think that's what we actually want. So let me just see if this now prevents a move. What is happening? Did that not recompile or something? Why am I not stepping through actual locations in the code? That's freaky. What the heck is what is that doing? Very nervous right now. That does not look like a sane debug step. Where am I at on 4Coder these days? I mean, not 4Coder, Remedy BG. What version? So 3.5 is the latest version, and we are not anywhere near that. So that may be a mistake. Hold, please. Hold, please, while I download this from itch.io, which, as we know from Apple's lawyers in the Epic trial, is just, I mean, it's so risque. The itch.io store. Oh my goodness. What even happens at the itch.io store? Think of the children being corrupted at the horrible itch.io store that Apple is so valiantly and courageously protecting us from. Without people like Apple to prevent you from getting stuff on your computer that you were trying to get, I just don't know where we would be. I mean, thank God they don't leave decisions up to the people who bought the computer. I mean, that would be... Can you imagine allowing the person who bought the computer to decide what to install on the computer? I don't even know. That's just ridiculous. Totally unacceptable. And I'm just thankful that we have people like Apple to tell us what we're allowed to run, because without that, I would just be... I mean, it's a big, scary world out there. And I just don't know what I would do. I mean, I just don't know. I would just be a career criminal by now if Apple hadn't protected me from the horrors of the things on itch.io, like a debugger that I bought, that I use. I mean, it's unspeakable, really. So thank you, Apple, for all your tireless hard work making sure that I don't ever get to make a decision about what happens on a computer. It was great. It was really something the world needed, was more centralized control over decision making. That's a thing that everyone says is great. That's what people say. It's what people have said throughout history. If we just had a central authority that could tell us what to do, and Apple is helping to bring you that world, right? So it's good. It's great. Really, really pleased. Great company, Apple. Fantastic, Okay. Let's see if we can get better stepping here. I know that there was all these weird things happening with Visual Studio's PDBs and stuff, so we may just have needed... Nope, it's just busted. So I don't know what's going on there. Maybe X13 Pixels can tell us sometime. I have no idea why it is not able to step over those lines properly. But at least now it's not picking those moves, which is what I wanted to make sure of. But we kind of need to actually still see what the heck is going on. Because, I still want to go step through this routine and look for bugs and such, right? So let me before I go any further, let me run this in O2 and see what happened, right? Yeah, I have ordered new glasses. I hope they come sometime soon, but I'm not going to hold my breath on that. So you can see this is still in a bit of a bad state. So we're not quite out of the woods yet. We still got a pretty janky set of bugs in here. But okay. So let's see if we can't step through and clean this up. No, I didn't buy the glasses from Apple. You know, I don't do too much politics on stream, but I will simply tell you that like the arguments that people use for things are really interesting because you can tell that they're never arguments that they just like Apple and want that to be okay. They're not arguing about it because they actually thought through all of the consequences or analogies to what they're saying. They just like an Apple product or an Apple operating system or whatever, and they just want that to be okay. So they say something that they think is making an argument, but it actually isn't making an argument, right? Because a lot of people are like, well, as long as you know up front what it is, it's okay. Or it's a private company, they should do what they want, all those things. And you would never accept any of those arguments for anything else. You know? If somebody honestly said to you, like, you know, looked you in the eye and said, we don't need public accommodation law, consumer protection law, lemon laws, disclosure laws. We don't need any of those things. Because as long as a company just says, here is what we do up front, right? And some big long list of things that everyone agreed was horrible. You pick everything you want that's horrible, right? Every last little thing. You know, discriminatory, like we set which races are allowed to buy the computer. We say whether men or women can buy the computer exclusively. If it's completely broken when it gets delivered to you, tough. We're not going to refund it, right? Laws are there because a transaction should only occur under circumstances where the person gives you the money and you give them back a thing that is then theirs. And we have spent so many decades cleaning up all the authoritarian crap that companies or governments or everyone else tried to do using all those same excuses. It's just a private party. You knew what it was ahead of time. It's like, no, we don't want private parties doing these things. Being able to purchase things and then you own them is something we fought for. Not allowing a company to discriminate, to censor, to decide what you can do, to take back something you bought, those are things that were in the law. And people just forget this. Somehow in their mind, none of those things existed. The world just started and companies were these beautiful benefactors that never discriminated against anybody, that never shipped defective products and didn't give you refunds, that never treated their workers horribly, that never did any of these things. So why are you getting so upset about this? Why do you want to tell this private company what to do? Have you read a book? Like, I don't know what to tell you. Companies are horrible. You want things like capitalism to have markets where consumers can make choices so that we can allocate resources properly. That's it. We don't want corporations competing over controlling their users. That's absolutely ridiculous. Read a frickin' book if you think that's a good idea. It's nuts. So none of those arguments to me hold any water at all. It's obvious that you need strong consumer protection, strong things that say that a consumer is a person who presents their money and receives the product, and that is the end of it, and the company gets no say in who that consumer can be or what that consumer can do with the product after they purchase it. That is up to the citizen and their government alone. And as a corporation, what you get to do is hand me the frickin' thing I bought. Yet competition is not what you think it is. Competition is a way of allocating resources, right? And once those resources get allocated, you end up with lock-in. So competition doesn't solve mistreatment. If it did, you wouldn't need any of these other laws. If competition worked the way that you're saying it does, you wouldn't need any of these other laws. You wouldn't need anti-discrimination laws. You wouldn't need Title VII, right? You wouldn't need consumer protection laws. You wouldn't need courts at all. It would just be competition. Nobody believes that's true. Nobody. People just say it because they want people like Apple to be okay. They just like Apple. Competition, all it does is at the outset, it allocates resources somewhere. That is all it does. It can't do anything else. It does not fix social problems, period, right? Once you have resources allocated, you can't really change it very effectively. Competition doesn't do that. It's why you have anti-monopoly law. It's why you have all this stuff. I don't know what to tell you. Like, if you've never heard of AT&T, like, have you never heard of, like, what trusts were? Have you never heard of railroads? I don't know what to tell you. I love capitalism. I think it's a great way to allocate resources. It only works when you have already created the circumstances under which you want that competition to occur optimally. You simply cannot trust it to solve any other problems for you. It's not what it does, right? It's not what it does. All right, let's do one more step through. So this test is pretty obvious. That just does all 8 corners. I don't think there's much, because that just got wholesale imported from the other thing. No matter what that returns, this should always terminate. This loop should always terminate fairly. So we shouldn't have to care about this. We should just assume that whatever this returns, it returns. We never have to think about it again, right? And then if there's bugs in this, that's a separate thing that we would debug. So it's this part here that we actually care about, and it's the update best termination criteria. That's the problem here, right? This probably doesn't work right or something. So we need to make sure that this correctly always terminates. You know, it can't ever get into a loop where we're like constantly where we keep trying new and new cells. We need to terminate after a few simple steps, right? So let's go ahead and see what we're doing here. So we look at best. We look at best and we see that we have a distance squared of 0, which means that this doesn't need to happen, right? So this one's just going to exit out immediately and we don't care. So what we want to do is get to a one of these that doesn't work as well, right? So we want one, yeah, like that, where there actually is a distance. So this means we're trying to move from this cell to another cell, right? if this makes sense. And we just want to go ahead and someone said, I love capitalism when it works for me, screw other people. Yeah. Yes. Like, that seems to be what people say, right? They don't seem to want to engage with the fact that all these laws were made for a reason. You had to make these laws because competition didn't produce a fair marketplace for humans, for citizens, in the worst possible ways, in horrific ways, right? And somehow they just throw that out the window because they like Apple or something. And it's not just Apple, it's other people they argue this for. It's not okay, right? I am not a person who wants to throw out capitalism. I think it does a great job of optimization, right? But it has to be coupled with restrictions on what can be optimized. Because if you just let capitalism optimize, it will optimize on everything, including screwing the customer, right? Because as soon as a corporation can start to screw a customer, because like they don't have enough other options, or the cost of the barrier to entry to that market grows too high, it will just straight up optimize screwing the customer all the way down to zero, right? And so history shows this unequivocally. Like, there is no argument that that is what happens at all from anybody. Even people who are extremely pro-capitalism, which I am, right? I think it's a great resource allocation strategy. There are no examples that I know of in history of allocation strategies that beat it. But you can't just expect it to solve all problems. It just optimizes. That's all it does. If you don't set up your optimization problem first, it will optimize all sorts of things that are horrible. And that's exactly what you're seeing. That's exactly what Apple does and Facebook right now. That's what you're seeing. You're just seeing them optimize variables that humans really shouldn't optimize. And you just need some laws. You need some laws that say, nope, we're not going to do that. You're not going to collect information from customers. You're not going to get to decide what software runs on what hardware. We don't want that to be optimized because we are going to let the citizens decide what they do with what they purchase and be free from your intrusion, right? In my mind, that is a very, very valid argument, and you can have arguments against it, but one of them is not, it's a private company or capitalism always works. Like, those are not real arguments because it's so trivial to point to all the ways that that's not true. And you obviously disagree with that because if you really thought that was true, you would argue for repealing all of this stuff. You'd argue for repealing Title VII. You'd argue for repealing all public accommodation sections in all state laws. You'd argue for repealing all workplace protection safety because if it was just competition that solved these problems, you wouldn't need any of those things. Right? So if you want to make that argument that we repeal all of that stuff, make it. But if you aren't willing to say that all of those laws need to be repealed, then your argument doesn't make sense. So you need a different one. You need a different argument for why you think it's okay for corporations to do these things. That they are a corporation is not a valid reason because there are so many examples of when you wouldn't have accepted that argument. So you need a different one. You need to explain why this thing specifically benefits the public good more than it hurts. You need an actual, carefully described argument for why having a consumer not own a device they buy is better than having them actually own it, right? Why you think that allowing a corporation to control a customer's decisions after their purchase is a positive social human development that you support. So that's what you got to do, right? Yeah, the Handmade Political Podcast. No one's going to go on that podcast. That'd be a lonely podcast with me just complaining about stuff that seems so obvious that I don't even know why I'm explaining it, because it's like I don't even understand how people get to the other conclusions other than simply this is what we wanted. Like that, I can't even wrap my head around people who argue for Apple's behavior. Like, the only thing it sounds like to me is I just like Apple products. That's all I hear, because I don't ever actually hear an argument. All of the things that they say make no sense. If you wanted a infantile storefront, you could just get one. Like, nothing's stopping you. Like on Windows, if you want, you can just choose to only install games from Steam. Nobody stops you from doing that. If you think that Valve is doing a better job of that, you never have to go to itch.io. Right? I don't know. If your argument is like, well, grandma, and she doesn't know, it's like, okay, are you actually saying that the world should be governed in a way that is entirely determined on whether you think your grandmother can handle it? Like, what? I mean, in that case, we wouldn't have cars, right? Because you know that grandma's going to get in an accident. That's why we took away her license. It's so weirdly, it's like an attic filled with like cobwebs in the part of the brain that was supposed to come up with an actual argument, right? Anyway, so this is the part of the code, going back to here, that I don't really know, and it's hard for me to step through because it's doing like this weird thing. I'm not sure if what's happening there is we're stepping over these because they're not triggering, and let me just see if that's the case so that we at least know what we're looking at, because the debugger's doing a weird thing there, and I just don't know why it's doing that, right? Oh! Well, first of all, these are backwards. That should not have caused a problem, though, so that's a little scary. So we're still buggy, but we forgot the not. Forgot the not. I can't even blame that on the politics because I wrote this before the Apple garbage. So I think in here we've done the occupied. We do the not occupied for all of these. This is still buggy though, because it should have still always terminated. So it's still not. It's not right, you know. We must still have a bug in how this works, separately from that. Oh, and it steps right now, though. It steps right now, so we can actually see it. Okay. So it picks up the bests. If you can do it, it's picking up the best. This one's a distance squared of 0 anyway, so we don't have to care about that. And we'll want to look at one that actually has a distance squared, like that one, so that's good. When we produce the distance squared, let's go down here. When we produce the distance squared, we can look and see how we do. So we look here and we say, okay, are we going to update the best min corner based on a diagonal move? Let's see. Let's just try to think it through and see what we would expect. Like is this something we think should be happening or not, right? So here's the place we're trying to get to. We're trying to get to this 2p here. And we're starting off at this min corner. So you can see that like the min corner that we're trying to get to and the place that we are now are like, we're totally in the right location, except for the y. So what we want to do really is just move backwards in y. We just want to go negative y, right? So let's take a look at what happens when we update best. You can see that that would have got closer, which may be true because it's a diagonal move. What we want to do here is that probably won't trigger. This should trigger, hopefully, and it did. So that's hopefully the one we pick, and it is. So now we accept this new min corner, the best min corner here, which is a 1y move, right? Although it's not Oh, yes, it is. I'm sorry. We're moving from or Eggman corner. Yes. So that should just move, hopefully, along that voxel now. And that's it, right? Hopefully, it will just go until it gets close enough to count. And we'll see if it terminates. Okay. Oh. When we moved that out of the loop, kind of got to reset the move condition, right? Yeah. We could just check to see if the minimum distance decreased. That might be better. But I think we're good now. That was probably the only problem. The routine probably still has tons of bugs in it. We'll look at them next week. Let's see what the status is if we run it now. Hey, look, it's running. You can see that it's moving in the direction it should, but it's only moving like one voxel step. Like, that was weird. It's like do we not return the right? Oh, it's because we're never setting this. So when we leave this routine, best needs to create that best cell. So this thing here, so like, this is probably not exactly the way you would want to do this, but it would be like, that we weren't actually using the result from that, and we want to, right? So let's see what happens there. So there's our like collision detector, maybe collision detecting. We don't really know. So it looks like that's able to penetrate into the wall in a weird way. So we're not out of the woods yet. I think we're in good shape, but we're not out of the woods yet, right? We're getting there, but not yet. So I'm gonna leave it there, and we'll go we'll go ahead and pick it up next time. Oh, the stream title is always a joke. I just randomly said it. Oh, hey, X13. Yeah, it oddly enough changed when I switched to the knot. So it must have been something that Visual Studio's PDB was outputting, right? Like, because when the code changed, it stopped happening. So it's some kind of weird PDB thing, probably because of the multi-line OR statement. It was in debug mode. It was a debug PDB, and it was when you do it without the knot. And I don't know what was going on there. Right? So, can you explain how that 0.125 thing works? Sure. So, when you are using floating point numbers are basically just if you think about how you represent decimals, like regular numbers that we think of as humans, if you think about how they're represented in binary, you have bits that represent powers of 2, right? So when you're trying to represent a number that's not fractional, it's a little bit easier because you're just thinking, oh, I've got the digits. If I want to write something like 9, right, then I just say, well, that's going to be like a 1 plus an 8. So I set the 1 bit and I set the 8 bit, and now I've got 9, right? When you're looking at fractional values, that is not how it actually works. The way that fractional values work is each one of the bits divides by that power of 2, right? So if you set the bit for divide by half, you get 0.5. If you set the bit for dividing again, next place down, you would get, 0.25 or whatever, right? So you can, and this is not quite true because this is not fixed point. There's an exponent. So what you're actually doing is locating around one of those. It's a little bit hard to explain, but without a diagram and going into floating point numbers more. But you're finding the power of 2 that divides to as close as where you are, and then, right, you're putting in some mantissa on top of that, right? So no matter what you do when you're talking about dividing by powers of 2, you can never divide you can never get an exact fraction if that fraction could not have been expressed by dividing by powers of 2. You see what I'm saying? Right? So if you want to have something that has a divide by a power of 5 in there, which is what 0.1 would be, you're never going to get it because no combination of divides by powers of 2 will ever get you a power of 5, right? 1 over 5 cannot be represented by any combination of 1 over, 2 to the something times 2 to the something times, whatever kinds of things, right? You know what I'm saying? So if you are setting up something like a grid step, you can get your numbers to be exact by setting that grid's distance to be a power of 2 divide, right? So the reason I picked 0.125 was I wanted the numbers to not have all these trailing fractional parts, because if I pick like a decimal number, they're going to. Because it's the computer just trying to represent it as close as possible, and it's getting really close. Like, don't get me wrong, but it's not exact. Whereas if I just pick something that's a straight up easy divide by a power of 2 of some kind, then that's just trivial for it to be exact. It just sets the exponent to that, and that's it, right? And you've got it. Doesn't matter how many bits of precision in the mantissa there are, it just works, right? That's really it. There's also like a standard reference for this stuff. That's the one, but let's use oops. I'm getting binged here. So here you go. This is like the sort of standard reference, right, for this sort of stuff. Which you can peruse. Oh, and Mike Biddlecombe was saying that Bruce Dawson has some posts on this. I have not read that, but presumably Mike can post the link to him. It looks like someone else posted a floating point guide link as well. How much of a difference can this minute computation really make in real time? Are you talking about the 0.125 versus 0.1 thing? Is that what you're asking about? I'm not sure what you're asking. Is that what you're asking about? So, I just in case it wasn't clear. Well, I guess which it wasn't. I didn't change those because I was afraid that the math would work poorly. Although maybe you get some benefit from that as well, but I did it so I could read the numbers easier, right? So what happens is when you look in the debugger and you're trying to read numbers, if I set this thing, right, to 0.1, you know, and I'm going through the debugger and I'm trying to read it, then the debugger is just pulling values out of the stack and showing them to me. It doesn't know where they came from or if they should be rounded or anything like that. It doesn't know what I'm writing, right? So it's just going to show me the value, the floating point value. And I'm going to see all of this crap, right? That's all you're going to see is that kind of thing. And the reason is because it was trying there to say 0.7. But you can't represent 0.7. So the actual floating point value is not 0.7. And if the debugger rounded it to 0.7, you'd be pretty mad because it's lying to you. You're like, that's not what's in. I know 0.7 is not in that floating point number because you can't make 0.7 in a floating point number, right? So it's all I was doing was just making it easier on us because I know we're going to debug this next. I wanted to debug a little bit today, and then I know that's what I'm going to be doing is reading through that and being like carefully like analyzing what's going on. If I set it to an easy divide power 2, all I'm doing is buying myself a little convenience because now when we look at the values, well, if it actually, did that not actually compile? There we go. There we go. Now, when we look at the values, what you can see is that, well, and this is a bad example because the 2p, I shouldn't have picked this. The 2p is the thing that comes in from the engine, which can be anywhere. This is actually the part I was talking about. I should re-show it to you because I had the wrong thing open. Sorry about that. So at 0.1, we look at what the corner is that it finds, which is the thing that it's, aligning to. And you can see you get all these like 0.2, 0.2, 0.2, right, kind of things in there. And as I go through it, right, when I step through, I get weird 12.2999999, right? And so all I was doing, the only thing I was trying to do is say, look, let's just always use a step size that happens to be exactly representable in float for legibility. That's it. No point to it whatsoever. So now look at, they're all nice and clean, right? That was it. I don't expect the math to come out particularly much better or something, although that can happen depending on what you're doing, right? So yeah. How long have you been working on this project? I don't know how to add it up. So we only 100% of the programming happens on stream, and we only program a few hours a week on the stream. But probably at least 1,000 hours, maybe. If you put that into work terms, like how long I've been working on the project, so like, where's the speed crunch thingy? So I don't really know, but maybe it's something like 1,000 hours. So if you worked, I don't know, 30 programming hours a week, and the other 10 hours you were in really bad meetings where people said stupid stuff to you, it's about 30 weeks, let's say. So we were working on it, oops, about 2/3 of a year if it was real work. So figure 2/3 of a year worth of work has gone into this. If you count depending how you count it, on-stream programming is harder than off-stream programming. So, New to this, thank you for saying that it looks like a render. I was proud of the lighting. I'm not gonna lie. I was proud of getting the lighting set up. I went many years without ever having any lighting, and I was like, we're gonna fix this. Yeah, well, we need at one of these streams. We gotta just have a meeting. Just, we'll get some of y'all on the chat. We'll like use a Discord room to get like 10 people in the thing, and the only rule will be that for the entire time nobody can say anything provocative, interesting, or useful. Like everyone just has to like say stuff like, how are we going to factor in the user experience to this piece of code, or like just you just have to say like vague, unproductive, unprovocative comments for like an hour, and make sure that nothing is achieved, and then we can call that like our official handmade meeting. Izio Auto Revs, I don't know how to pronounce that. It's just mirrored. Bullminator, totally. Galactus. It's Galactus's pain. Ezio Auditora. Ezio Auditora. Something like that. All right. Yeah, I agree. Dynamically should be said. Scale. We should spend a lot of time worrying about if it's going to scale. We should just say stuff about, is this going to scale? I think this will scale. It will scale better if something, we gotta be scale's gotta be in there. Dynamic and scale, very important. Maybe we can just dynamically scale. Everything will be very dynamic and very scalable and very dynamically scalable, I think. Oh, Ezio Auditore is the main character from Assassin's Creed 2. Okay. All right. I think I'm pretty happy with how that collision routine is coming. I'm pretty comfortable to say that like maybe next weekend I think we'll be able to clean it up and have something sort of working. But who knows? That could be a lie. We'll see. All right. Thanks everyone for joining me for an episode of Handmade Hero. It's been a pleasure coding with you as always. If you do want to follow along with the series at home, and maybe you want to go see if you can make sure that routine works before I get to it, you can always pre-order the game on handmadehero.org, and it comes with a source code, so you can play around with it if you want to. And yeah, that collision detection routine I think is in pretty good shape. It just needs to be gone through with a fine-tooth comb. So when we get to that, I think we'll be happy. And then we can do some battle code, which we don't really know what we're going to do. That's game design decision stuff, which is not really what I do. But we'll make some decisions. Love Galactus. We'll push this out a couple years. So until next week, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.